Yesterday, we introduced waves, and we talked about two different kinds of waves and how waves, really what they do is just move energy from one place to the other. You jump off the diving board into the swimming pool, the person on the other side of the swimming pool that's laying down on an air mattress just getting some sun in a few seconds starts bobbing up and down. How did that person start moving? Well, that person received energy from you, but you never actually touched that person. The energy had to be transferred some way from you to that other person. It was transferred by a wave. You hear my voice right now. There's energy coming from my larynx, my voice box, kinetic energy coming from my larynx that ends up being transferred to you, but I'm not touching you right now. So how does that energy get transferred? It's transferred by a wave, by a sound wave through the air. Waves transfer energy. That's what they do. Now, there's two main kinds of waves. We've got the transverse wave, and we've got the longitudinal wave. Where we've got the bumps and the dips, or where we've got the areas of high density material and then low density material. Now, let's say both of these waves, this transverse wave and the longitudinal wave, are both moving to the right. The energy is being transferred from the left side of the board to the right side of the board. Can you tell me in the first case which way the particles are moving? The particles aren't moving from this end to this end. The energy is moving from this end to this end, right? The particles aren't moving from one end to the other. Okay, when we tried the slinky yesterday, used the slinky yesterday to send a wave pulse down to Haley, I think it was, right? Haley felt it, but the section of the slinky that I was holding on to didn't go all the way down to Haley. The energy went down to Haley. The section of the slinky, or the particles in the slinky themselves, moved which way? If you got a transverse wave, it was up and down. It was perpendicular to the direction of motion of the wave. Does anybody remember specifically what type of motion that those particles experience as they go back and forth? Here's your hint. As they go back and forth, back and forth, back and forth, perpendicular to the wave? No, not reciprocating. What have we looked at before wave motion here? What have we looked at for the couple of days previous to yesterday? Pendulum, yeah. What kind of motion is pendulum? Simple harmonic motion. So each of the individual particles experiences simple harmonic motion. Okay, the net effect of that is an energy transfer from one end to the other through this wave. Now, there's simple harmonic motion that's taking place within the longitudinal wave as well, but that simple harmonic motion doesn't go perpendicular to the direction of motion of the wave, rather it's parallel. So each of these particles is vibrating back and forth parallel to the direction of motion of the wave. Let's label a couple of things on this now. What's this called right here? What's that bump called, that hump called right up here? It's called the crest. We got 3 of them drawn in this case, right? But you could have 1,000 of them, or you could have 1 of them. It's a crest. It's the bump of a wave, the top of a wave. The bottom of the wave down here is called what? Think of the pig eating. It's called the trough. We got 3 of them here, but again, we could have 1,000 of them, or we could have 1 of them. The amplitude of a wave is related to the energy of the wave, right? The amplitude of the wave is defined as the height of the wave. We're going to measure the amplitude from here, from the top of the wave, to where? Tell me when to stop. The amplitude of the wave is measured from the equilibrium position, or the natural position, to the top of a wave, or from the natural position, equilibrium position, to the bottom of a trough. Either way. Okay, the amplitude of the wave, the height of the wave, that is related, that's an indication of the energy that's possessed by a wave. And finally, the wavelength, which is the distance over which the wave repeats itself. It's one complete cycle. The distance for one complete cycle, not the time, but the distance for one complete cycle. Let's start the wavelength right here. Tell me when to stop. From one crest to one crest. Or you could have went from here to here. Or you could have went from here to here, or from trough to trough, right? The distance over which the wave repeats itself, as soon as you're back basically to where you started, that's one complete wavelength. And that's going to be measured in units, or sorry, in meters, right? All right, let's look at the bottom one here now. There's not really much we're going to label on this. We could label wavelength, amplitude, and so on, but it's a lot harder to visualize on this just because of the way these type of waves look. Okay, the only thing that we're going to physically label on this graph or on this diagram for us is going to be compressions and rarefactions. Where's the compression? Okay, I'm going to start moving my finger around here. I'm going to start moving this pen around here actually, and I want you to tell me when I reach a compression. Yeah, that's a compression. Okay, that would be a compression. That's a compression where the density of the wave is higher. So if we're talking about the slinky wave, which we saw yesterday in the demonstration with Haley, right, where the slinky was really, really close together, that was a compression. If we're talking about sound waves are longitudinal waves, by the way, as well. You can't get transverse waves through a gas. Think about that. The particles have to be connected in order to get a transverse wave moving. You can't get a transverse wave through a gas. It's impossible. A sound wave must be a longitudinal wave. It's areas of high density air and then low density air following it. Okay? That's what you hear. That's what causes your eardrum to vibrate, is these compressions and rarefactions that are coming from my larynx. Yep, Haley? Yep. Yeah, be careful. The way that I have this drawn, it's not great. It's just the best I can do. This is not supposed to be like crests and troughs. It's just the slinky or whatever material it is, the particles are further apart and then closer together right there. So if you wanted to measure the wavelength down here, we don't normally label it on there because it's a little bit harder to visualize than it is up there, but you could go from the middle of one compression to the middle of the next compression. Or you could go from the end of one compression to the end of the next compression. Or what are these things called in between the compressions? Rarefactions, not refractions, but rarefactions. R-A-R-E-F-A-C-T-I-O-N, rarefactions. It could be from the middle of a rarefaction to the next rarefaction. I wasn't going to show you this picture, but I will. If you were to take a longitudinal wave like we see up on the board here and plot a graph, not show you what the wave looks like. This is what the wave physically looks like. But if you were to plot a graph, not of position versus time or position versus position, like we had y position versus x position like we had for the first graph yesterday, but rather the density versus position, then this is what it would look like. You would find that compression is high density. Then it goes down to low density. Then it goes up to high density. Then low density. Then high density. So the density versus position on the x-axis would end up giving you a graph that looks like a transverse wave. And in that case, it would be easier to see, that a wavelength goes from the middle of a rarefaction to the middle of the next rarefaction, and so on. Okay? We probably won't see this on a test, density versus position, but again, sometimes it is a little bit easier to visualize things like a wavelength and so on. Right? We also yesterday talked about the mathematics, the basic, at least, mathematics of wave analysis. We said that waves carry energy, not particles, and that energy travels at a constant speed. That is, it travels at a constant speed unless it goes to another medium. When we go from deep water to shallow water, the wave changes speed. Okay, because it's going from one medium to another medium. It's two different media. When light goes from air to glass or from air to diamond, it changes speed. But as long as it stays in the air or as long as it stays in the diamond, it travels at a constant speed. So we can represent the transfer of that energy, the wave motion, by saying V is equal to delta D over delta T, unless it changes mediums, unless it changes materials. We also said that The distance over which the wave repeats itself was lambda. And the time over which the wave repeats itself, d over t, the time over which the wave repeats itself was what? Yeah, the period. So v is equal to lambda over t. But we also said, this one was on our data sheet, right? This one wasn't. We also said that t is 1 over f. So this equation becomes v is equal to lambda over 1 over f, which, if we simplify that a little bit, becomes f times lambda. That one's on our equation sheet. We call this the universal wave equation. That's the name for that equation. Most equations don't have a name. Okay, this one does. It's the universal wave equation. Final thing before we take a look at the questions that we had yesterday. There are 3 variables in this equation. When a wave has been produced, goes, travels, maybe it changes mediums, maybe it goes from deep water to shallow water, maybe the light goes from air to glass, maybe whatever, okay? One property there, one of those 3 variables must stay the same, but the other 2 can change. Which variable is it in those 3 that must stay the same? Once the wave has been made, this one never changes. Sorry, Tony? The frequency, good. When light goes from air to glass, it slows down. It slows down dramatically, actually, by a factor of about 1/3. But the wavelength also decreases by a factor of about 1/3. What doesn't change? The frequency. If you shine red light through air into glass, it will still be red light when it goes through the glass. Okay? Frequency doesn't change, speed and wavelength can if you go into a new medium. As long as you're still traveling in the same material, light stays in air, keeps going in air, not going to change speed or wavelength either. But when it goes to something different, it can change speed and wavelength, just not frequency. We're working on some questions yesterday on page 409. Any issues with those questions? 409? Yeah, absolutely. Number 3. Number 3 says a fisherman anchors his dinghy, his little boat, in a lake 250 meters from the shore. Let's draw this. Okay, here's the shore. Okay, and there's the water, and he's anchoring his little boat. He's anchoring his little boat a distance of 250 meters from the shore. The dinghy rises and falls 8 times per minute. Now, this is one of the things that people get mixed up on, the difference between frequency and period. Frequency is the number of cycles per second. Period is the time for one cycle. So I don't care what you record here, frequency or period, but just know what you're recording. If we want to go period, then we would say time over number of cycles. Okay, because it's seconds per cycle. If we want to go frequency, then it's cycles over time. I'm going to go frequency because I think that's what I'm going to end up using. Frequency is 8 cycles. Goes up and down 8 times, right? Per minute. The time would be 60 seconds. So 8 cycles per minute. That's going to give me 0.1333 hertz. Or 0.133 up and downs per second. Basically, about almost a tenth, a little bit more than a tenth of a cycle in 1 second. Now, it takes the wave 3 minutes or 180 seconds to go to the shore. We want to know how far apart the wave crests are. We want to know this distance right here, how far apart the wave crests are. What variable is that we're looking for there, Aiden? Yeah, it's lambda. So we're looking for lambda there, the distance between the wave crests or between troughs or distance over which the wave repeats itself anyways. All right, everybody's got a place to start here, especially since we kind of went over this yesterday. Where do you want to start? Tell me one place, please, to start. Caitlin, where's one place to start on this question? Good. That's a valid equation, right? So even if it doesn't lead me to the answer, probably will, but even if it doesn't lead me to the answer, it's fine to write that down and try it. Worst case scenario is it doesn't work for us, we try something else, right? So write down V equals D over T. Sounds good. Hey, look, we know D and T, so it is going to get us something. Now, it's not what we're looking for. We're looking for wavelength. It gets us speed. Maybe that's helpful, maybe not. D is 250 meters divided by 180 seconds. What's that going to give me? What was it there? 1.39? 1.388? Okay, there's the speed, 1.38889 meters per second. All right, good. Caitlin, you got something. Okay, now what we're looking for, probably going to help me. Even if it doesn't, big deal. You solve for something that's legitimate. It's just not the answer we're looking for. Atlanta, anything else you can try here? Yeah, that upside down Y, lambda, the Greek letter. Yeah. The universal wave equation, right? Looking for lambda. We got the speed. Caitlin got us the speed, 1.3889 divided by the frequency, which is, oh wait, do we know that? Yeah, 0.133. Lightning fast calculation here, and we're going to get, it's going to be 10 point something. We'll round that to 10 meters, right? Lightning fast calculation in our head, or lightning fast peek at the answer over here, and we get 10 meters. Okay? Is that okay? Yeah. Let's take a look over the break at page 410, number 1 to, I think I said 8, 1 to 7. Yeah, 1 to 7 and 9. All right? You might even have a few minutes towards the end of class to work on this, or you might not. You got 2.5 weeks coming up, right? 2.5 weeks, I should give you more. Let me see if I can find some more homework for you to do. No, I won't.